Warning, knowing derivatives in the power rule might be helpful for this video. Instead of doing any normal thing with derivatives and graphs, let's look at some sequences. A sequence like the squares, 1, 4, 9, 16, 25. The second grader inside of me immediately wants to take the difference between each term for 3, 5, 7, 9, then do it again to get a bunch of 2's. Now, if we take the first row as x squared, we can actually identify the next two rows as each of the next derivatives. The row above is 2x, just if the indices were shifted by 1/2, going halfway between 1 and 2. The last row is just a constant 2, which matches the second derivative of x squared. Let's see what happens if we add cubes instead. I'll add an extra term for 1, 8, 27, 64, 125, 216. The differences are 7, 19, 37, 61, 91. And the next set of differences are 12, 18, 24, 30, which give the third derivative of 6. If the second row started with a hypothetical index of 1.5, this third row should start at 2, which fits perfectly with 6x. However, the problem is that the first derivative here doesn't work so well. Decimal indexes aren't very nice when we have to square them. The values you'd get are 6.75, 18.75, 36.75, 60.75, and 90.75, all values that are just 0.25 short of what they should be. Given this, let's just add a small 0.25 called an adjustment inaccuracy and continue without issue. While going to quartic might be the next logical step, let's instead see what happens when we modify this with coefficients. 2x squared doubles all the original terms and doubles each derivative. This matches with the double differences. Makes a lot of sense. The same thing works for 2x cubed, all the differences double, just like the derivatives. The only complication is the 0.25, which also needs to be double. But whenever we multiply, we can think of it as stretching every term that we had in this initial difference pyramid. While this is a mostly pointless exercise, what we have here is a terrible solution for sequences that line up with cubics. We can use a third derivative for the cubic term, the difference between the second derivative and what it would be as just a cubic for the quadratic term, and then map the rest of it out for an equation. Let me show you how it goes. Let's model with the equation 2x cubed minus 4x squared plus 3x plus 2. Our sequence goes 3, 8, 29, 78, and 167. This fifth term isn't necessary, but I'll include it to show that the third derivative is constant. So our first derivative terms are 5, 21, 49, and 89. Second derivative terms are 16, 28, and 40, which gives a third derivative of 12. 2 times the 6 we had with x cubed, so 2x cubed is our first term. Our second derivative terms for x cubed went 12, 18, and 24, but these are doubled to get the 24, 36, and 48 for 2x cubed. Subtracting that off from the actual second derivative terms leaves a constant negative 8. This gives us the negative 4x squared, which is half of negative 8. For the first derivatives, I'll pull 7, 19, 37, and 61 from x cubed and double them, then take 3, 5, 7, 9 and multiply by negative 4, and then subtract these from the original first derivative to get a constant stream of 3's, the coefficient we want for x. And now we have every coefficient except the last one, and to shortcut it, we can plug any number in and calculate that term to get the constant should be 2. As a note, if you want to speed this up and actually use it, don't even bother with the later terms and assume you get constants on the way down. But I doubt you'll remember these numbers I had to pull out in order to solve this in a reasonable setting. Anyways, I hope you enjoy these derivatives and sequences, and I will see you some other day for some more stupid math.